Hello all, welcome to this session. My name is Deepak Cherian, and I'm here with my co-presenter Julius Biseca to introduce you to the Pangeo community. We are both oceanographers. I work at the National Center for Atmospheric Research, and Julius is at the Lamont Doherty Earth Observatory. First, we'd like to thank the organizers of this session for giving us this wonderful opportunity to speak. I'll confess, I was a little overwhelmed when I was first asked to introduce Pangeo. And so I sat down and made a little word cloud, very approximate and very incomplete word cloud of all the things that I associated with Pangeo. You'll notice that there was a lot of technical terms like analysis ready, cloud optimized, things like cloud native analysis. Maybe you think of Pangeo as crunching big data sets using open source scientific software such as Xarray, Dask, and Czar. Maybe you've interacted with the Pangeo discourse forum or Pangeo data catalog, or even through various teaching and educational activities. And so this was quite overwhelming. And so I thought it would be good to start with my story of how I came to Pangeo. In 2010 to 2016, I was a graduate student running idealized ocean simulations. And because I was doing my own simulations, I could generate as much data as I wanted. I ended up archiving about 12 terabytes, so roughly 100 simulations. And I think there were about 100 to 200 gigabytes each. I was analyzing this data first on my laptop, and then on various servers, and these simulations are run on NCAR's HPC system, then called Yellowstone. Analyzing it was not easy. I found that I had to learn a lot of things, and there wasn't really a community with which to interact to learn those things. I'm sure I reinvented many wheels, mostly because I just didn't know what I was looking for, and I ended up solving a lot of problems on my own. In 2017, I started using Xarray, and this was really my first introduction to Pangeo. Then I was working with just some mooring data, so 5 moorings, just a few gigabytes at most, plus some satellite data sets and other things. But again, not that big. I was doing all my analysis on the laptop and it was fine. I just used NumPy, so things were just in memory. And so again, I just want to emphasize that this is small data. It isn't that big. In 2019, I moved to NCAR, and there I was started to analyze much bigger data sets. So here I really had to learn how to use Dask and other software like XGCM, and I started using Jupyter Notebooks a lot more. And so there was a big change at that point. And today I work with small to big data sets, anything from megabytes to terabytes. I analyze these data sets on laptops, local servers, HPC systems, or even occasionally I go up to the cloud and try a new idea with some data sets to see if there's something I can build a proposal on. And I do this with both observations and models. And the reason I can do all of this and kind of switch between all of these things very seamlessly is because the software is written like that, and it's a real strength of the Pangeo ecosystem. But when I was thinking about this journey, I came to a realization, which is that I was learning a lot. And so when I started using Xarray, I noticed that mostly from my MATLAB days, I picked up this habit of typing for always by default when I was starting a new piece of analysis. And so even before, I would start off with this very low level way of thinking, because you would always for looping over something, right? And it was just a matter of what, and then what you wanted to do in that for loop. Today, I don't do that. Instead, I try to think at a higher level. I ask myself whether I'm doing a binning operation, so something that would use Xarray's group by, or am I doing some kind of moving or sliding window operation where I would use rolling from Xarray. And this was really interesting because I realized I learned this whole new way of thinking about data analysis from a bunch of people who I'd never met, but whose ideas were expressed in the software through Xarray. And I thought that was really powerful. And this pattern I realized repeated again when I started learning how to use Dask and XGCM and Xarray all together. Then I learned from more complicated examples that you can find on the Pangeo gallery, and in particular the XGCM documentation. This was particularly relevant for me because I was starting to look at MIT GCM simulations. And these notebooks were great. They showed me how to do things properly, set things up, and run fairly complicated analysis. And again, you'll see the same pattern here. Again, I was learning from a group of people that had taken the time to put all this material together very generously. but I didn't talk to them, right? I was learning it from it in a very asynchronous manner and engaged with the material as I needed it to learn more and get more and more sophisticated as I was building more and more sophisticated analysis pipelines. And so I think this kind of story illustrates the idea of Pangeo as a community, and in particular as a community that is large, distributed, and does a lot of peer-to-peer learning, that a lot of people are talking to each other and telling everyone else about what they've learned. And so I think that idea really explains this word cloud. Is a large community with many interests, and people try new things and realize that you could take that new thing and plug it into the existing thing to do something entirely new. And there's a lot of people doing it, a lot of people trying slightly different things. And all of this, when you add up together, really lets you push the science forward. I think that is, to me at least, is the core Pangeo vision. And it also explains why you associate so many different things under the Pangeo umbrella. And so the one point I want to communicate in this talk is that I think it is appropriate to think of Pangeo as a large community that is doing a lot of peer-to-peer learning. And that helps explain a lot of these things that you'll see. As scientists, we should be familiar with this pattern because we do this all the time. On the left is a screenshot of one of my papers where the citations are highlighted in blue. And those are places where, as scientists, we engage the community, take ideas from the community, build upon it, and take it forward to come up with some new scientific insight that then we then talk about in the new paper, which then hopefully gets cited again, and so on and so forth. So this idea of building on existing efforts is really the core of science. And it's also the core of scientific software and analysis software. So on the right is a cell from a Jupyter notebook that I've been using. And you'll notice a lot of import statements. And I think it is entirely fair to view these import statements as places where we take ideas from the community and then build upon it in that notebook to come up with scientific analysis. So this is entirely analogous to what we do when we interact through the literature, except now it's in code. Usually that idea gets expressed in this kind of pyramid form where you have a bunch of software names, so Xarray and Dask, for example, and many more at the bottom. This is just a small subset. And then above that, you have little higher level software, things like XGCM or ClimPred or CMIP6 preprocessing that are a little more specific. That lets you do some things. And then at the top, there's a little bit of custom code that, where scientists put together all of these little pieces to come up with something new, right? So this is the big vision of things building upon things. But I think there's a really important piece that's missing from here, which is this whole community aspect that I touched on in the beginning. And so as scientists, we engage with our community through papers and the literature, right? We do citations, we read a lot of papers, we review papers, and then we come to conferences with expensive admission fees and optimistic deadlines. And there, again, we interact with each other and share ideas, right? But that is mostly about science. Very rarely I feel like is it about analysis. This session may be an outlier. But on the internet nowadays, we interact and engage with each other in a much more broader fashion through many platforms like Twitter or maybe the Pangeo discourse or even GitHub. And so on all these places, you'll start to see a variety of discussions taking place. A lot of it could be, I want to do X, how do I do X? Or like that example there about XGCM on GitHub is really about trying to find the lowest common pattern in a really complicated piece of analysis. And the idea being that we can take this pattern, abstract it, and implement it so that the next person doesn't have to re-implement it. They can just start from there and apply it to what they want. And so going back to that presentation of that idea of the inverted triangle, like I said, I think this is missing the community piece, and that's up here, which is how we interact with each other through papers, through conferences, through various online forums, and maybe even for your little project, you may have a bunch of shared Jupyter notebooks. The inverted triangles are intentional, just as in certain famous novels. It's meant to signify that there's a flow of ideas and knowledge from top to bottom and bottom to top. And by this, I mean, the software lets you try out new things and come up with new analysis that you then publish. And then maybe somebody reads that piece of analysis and decides, hey, I want to do this again, but instead I'm going to go find the common pattern that's sitting at the bottom of this analysis. And let's see if we can fit that in some of this existing software, like say CMIP6 pre-processing, or XGCM, or maybe even XRA, right? And then once that software is written, somebody else can come by and say, oh, hey, I know how to use this piece of software and it has this cool capability. Let me explore. And that kind of pushes the science forward, because now this person gets to try out something new pretty easily. And instead of working on implementing things from scratch, you get to just try new things and instead come up with new scientific insights. And so to me, I think that is the real Pangeo vision. It's this kind of interaction between code and software and people and science that this session is all about. And so I'd like for you to think of Pangeo. When you hear the term Pangeo, think of a community that is talking to each other, not just on online forums and through papers or various conference sessions, but also through code, right? And so these ideas can be expressed in many, many different ways. And it's really about taking it all together. And importantly, just taking things at your own pace. You don't have to do all of this at the same time. You can start small. I started with just XRA. And you can do that and just build up from there. And that's the whole point. So I'd like to end with this very nice slide from Julius. And to me, it really signifies that it really doesn't matter what computational platform you use. It really doesn't matter whether you work with models or observations of theory or big data or small data. It's really about the community. And it's really about interacting with the community and engaging with that community. And you can do that just by going to discourse.pangeo.io and asking a question or say, how do I do X? I'm struggling. Or it could just be, hey, I had a great success today and I did X and I've put this little new package up there. Why don't you try it out? And that's all really that's needed. And with that, I'd like to hand over to my co-presenter, Julius.
All right. After this great introduction by Deepak, I will now give you a demo of what is already possible with the tools the Pangeo community built. I will use the CMIP6 archive as an example here. CMIP stands for Coupled Model Intercomparison Project, and this is an internationally coordinated effort to model the future of the Earth system under different scenarios. It contains many different models, within them different runs, different members, different experiments. So it's really a huge amount of data. It also represents an invaluable amount of information and a ton of things to discover for scientists who want to dig into it. The most common thing scientists want to do with that data is sort of come up with some cool analysis, apply it to each data set, then aggregate these and visualize them. This is something you commonly see in the IPCC report, which is sort of shown here as an example on the right. So let's outline how this workflow would look like in an ideal world. Well, first you got to have an idea. Then you usually run some code to translate your idea to the data. And well, then you get some interesting results, interpret and hopefully publish them. And you in the community learn something. Well, but in reality, this looks quite different. You usually have to download the data to your computer first before you can analyze them. This works totally fine with megabytes, gigabytes, sure. Gets painful with terabytes. And when you reach the petabyte range, this really becomes unrealistic. And the petabyte range really is where we're sitting with CMIP6. Even on a fast internet connection, you end up spending days or weeks just to download the data. But okay, let's say you went through the horror of downloading and storing many terabytes of data. Now you're ready, right? Well, no, unfortunately, the CMIP6 data is not quite clean enough to just go into analysis. Here, I'm just showing one of several issues that the data sets are named differently. Well, that's easy enough to fix. But at this point, you've probably forgotten what you initially wanted to investigate, or at least a lot of your attention has been captured by this boring pre-processing. So you might ask, isn't there a better way? And well, there is. So the Pangeo CMIP6 archive in the cloud makes accessing giant amounts of data virtually instant with just a web browser. And CMIP6 pre-processing attempts to crowdsource fixes to these common data cleaning tasks. Since rarely anyone works with all of the data, this crucially relies on community feedback, or as Deepak would put it, peer-to-peer learning. In short, if you work or want to work with CMIP6, Pangeo Tools lets you focus on the science and not the data processing. I'm now going to show a quick demo and we'll then come back. So all I'm doing here is basically accessing the Pangeo intake catalog that is stored, basically gives you access to all of the CMIP6 datasets stored in Google Cloud Storage. I'm then going to select a couple of these models just to keep the time down that we need to process them. I'm only going to look at the historical runs and the strongly forced SSP 585 scenario. And then I'm also going to subset a couple of model members, because some of these models actually do have quite a lot of members. So this takes a little bit of time to load, but you can see that we're loading almost 400 data sets here, and we're taking about under a minute. So that's way faster than downloading the data set. What I'm doing then is post-processing, which is also part of the CMIP6 pre-processing package. And all we're doing here is sort of cutting the time to a common value, matching the metrics, which is a really handy function. Sort of the metrics we loaded is the horizontal cell area, which is not the same in all of the models, or not the same distributed across space. And so we need to actually weigh the sea surface temperature with the area. And then I'm just going to concatenate the members of the models if available, so that ends up as an additional dimension in the X-ray data set. You'll be able to see that here in a second once these steps are done. And then we can actually go to the meat of the computation. And really what I want to highlight, the real computation is a one-liner here. So we have a loop over all of these combined data sets, and we've done all of the work with CMIP6 pre-processing to set that data set up to really enable this absolutely simple computation. What we're doing here is we're taking the sea surface temperature, we're then using X-rays syntax to weigh that with the horizontal cell area, where we need to fill missing values with 0, and then take a mean over the X and Y dimensions, so over the horizontal space, and that's it. All else I'm doing here is pretty much the extra stuff. So I'm basically, let me just throw this on while I explain. I'm basically coarsening this to just like, this is just a visual thing, so we get annual averages a little less noisy, and then I'm just plotting. So most of this stuff here really is sort of configuring the plotting with X-ray and assigning colors to the different models. But like the actual computation is happening just in this step, and I really like how easy that actually becomes. We're gonna wait here a little bit. This is sort of the meat of the computation. Should take about a minute or so. We're timing this as well. You can see on the right here, little nice task graphs. You can see that there's like all the workers communicating with each other. You can see progress bars of all the tasks, and down here you can see all of the tasks sort of being processed in parallel for each of the models. Should be done fairly soon. All right, here we are. So this took about a minute, and what you're seeing here is basically the average sea surface temperature for a bunch of the models in different colors. Where available, we have the members sort of as transparent lines in the back, and the member average, or the ensemble average, however you want to call it, as a thick line. You can see there's sort of big differences between the different models, and it's up to you to identify what is causing that. But yeah, just to sort of drill that message home, we just went through 40 plus gigabytes of data in a few minutes. And if you're assuming that you have a fast internet connection and want to download this kind of data with like 20 megabytes per second, you would spend at least 30 minutes to just downloading the data. Wouldn't have even written any code or processed anything, just so to demonstrate how much quicker this approach actually is. And you also only need a web browser. Okay, so in summary, why should you use the cloud to do climate science? As you saw in the demo, it is really, really fast. And we all know that speed matters, because if things are too slow, most of us will move on to the next interesting idea, if you're honest. It is also open to anyone with an internet connection. So you really don't need a supercomputer to do cutting-edge climate science. This really opens up a new dimension of open science, where not only scientists from wealthy nations can create knowledge. We can enable scientists and stakeholders from around the globe to get involved and make science as a whole better and faster. In a similar vein, the cloud enables a lot more collaborative science. You also get to build on exactly the same data sets and can pick up where others left off. This results in less toil for faster and more fun science. Lastly, it really lowers the barrier to look into large data sets like CMIP6. I have one personal example where a friend of mine asked me if I know how well CMIP6 models represent subsurface pH in the Arctic. I had absolutely no clue, but I was able to send him some plots within 10 minutes. Unfortunately, he said they look horrible and that he would not be able to work with them. And I don't need to bash the models here, but it's just highlight that these sort of negative results and how quickly you can attain them are important for science. Think about how awful it would have been for me to waste several days on this. With the cloud, it's a quick look and a quick decision. Being able to quickly judge whether adding CMIP6 output to your study could help seems like a game changer to me. And ultimately, I believe it'll get more people involved with this phenomenal data set. I think it's worth reiterating Deepak's excellent point here. Pangeo really is a community to learn from each other with tools that help us do it. So I hope you are really stoked to get involved. There's many options to reach out with either feedback, questions, or just to try out the tools. Please check them out and join the fantastic Pangeo community. One thing I really want to stress is that I often get a question about sharing code. And I really want to emphasize that you shouldn't be afraid to share your code. I've never seen any code shaming going on within the Pangeo community, and we absolutely discourage any sort of this behavior. It is way more likely that you will get some helpful comments on how to improve your code, some cool tools to check out, or something else that might help you with your research. Communications about science are often much easier if you show your code and center discussions around it. So please consider this. On another personal note, just like Deepak and probably many of you, I transitioned from a MATLAB-based workflow to Python. As awesome as all of this stuff within the Pangeo community is, I know it can be really overwhelming at the beginning. My recommendation is always not to try to refactor and rewrite old projects. It is often difficult and often boring. Instead, try to start your next side project or your next project with Pangeo tools. As a matter of fact, why don't you just stay here now and start exploring CMIP6 data in the cloud? Either way, thank you very much for attending our talk. We hope to see you somewhere in the Pangeo ecosystem soon.